All right, welcome everybody. This is Fred Schenkelberg, and this is our Accendo Reliability webinar series, Fundamentals of Interpreting Test Results. And the more I thought about this one over the last couple of weeks, since I've been considering what to talk about and what to bring up, I ended up with a lot more questions than I did ideas or answers, but I think I got it distilled down to a handful of useful items that you can take away. This is something I'm going to veer off into pet peeve area here a little bit in some of my examples, because I see the ability to interpret results dealing way too much with blinders on or wishful thinking or ignoring the assumptions, the impact they have, things like that. So let's get into it. So welcome everybody. And like I said, before we hit record, we'll use the chat window. And if you're listening to the recording of this or the podcast version of it, feel free to get in touch via email or contact forms, or whichever works for you. I'd be happy to answer any questions. If I can get my cursor to actually move forward. One of the things about setting up testing, any kind of testing, is that we often make a lot of assumptions. And we do this in design work, we do this in manufacturing work, we do it in all kinds of different areas. But we have to make assumptions to simplify the problems that we're dealing with. And one of the key ones is that our testing will either replicate close enough or be translated into what the actual use conditions are, is the way people actually use our products. And that's a key assumption for a lot of our testing. And it's not the only one. We'll talk about a handful of others that trip us up all too often. Another part is that we need to think of the design of the test much like we design the product or design the system. It is not by any means pull it off the shelf and turn the crank and you have results. The likelihood of getting meaningful results with that process are exceedingly slim. So think through the design or the process you're using to create the results, the testing itself. How is that actually going to be put together such that you will get clear results at the end of the exercise, of the experiments? And then measurements. One of the things, and I don't mention this much more in the rest of the talk, but one of the things I found over my career is that this simple little tool of measurement system analysis, a gauge R&R, is by far the most valuable thing I think I've ever done. What I'm using to make the measurements in my experiment are giving me lots of additional error in those measurements, the ability to detect the change or the outcomes or the results that we're looking for in a meaningful way are completely fogged up and messed up and likely not to be correct. And so making sure that what you use to make the measurements is capable of making those measurements, that is accurate enough or precise enough or consistent enough or repeatable enough such that you can believe the measurements that you get. Now, it's one thing to pick up a ruler and say, oh, this pencil is 6 inches long, give or take half an inch, maybe just perfectly fine to make that quick measurement. But when I'm picking up a pencil, I usually don't really care about how long it is, unless I've sharpened it 27 too many times and now it's only a 1/4 inch long. It's hard to write with it. But the idea is that if the measurements matter, which is the only reason I would expect anybody should ever do testing, especially reliability testing, is that they matter, they're going to be used for something, is that the underlying measurements that we're using are good, are very capable of giving us good measurements. And well, let me move off of that. There's so much more to it, but this is hopefully, if anything else you take away, is go do measurement system analysis, go do a gauge R&R on your next test setup. So here's the first question for you. What's the purpose of testing? And here testing, I'm thinking of the stuff we typically do in the reliability world. Environmental testing, some of us do some standards-based testing or regulatory type stuff. Some of us do accelerated life testing or ongoing reliability testing, or some of us do HALT, HAS, we do screens, we do all kinds of different things. But what's the purpose? Why are we doing all this testing? And for those that, well, I think just about everybody here I've seen before, so the chat window is open and that's where I'll be looking for it. Yeah, Robert, you've seen some of my other presentations. Yeah, to help to inform a decision is a purpose for doing testing. Now, luckily, nobody is going to say, yeah, predicting performance, is it going to last long enough? What's its expected failure rate? That's good. It's not because we did it last time. That's usually not a good purpose. It's, oh, we happen to have a lot of prototypes. How about we go do some testing so we use them up? That's usually not a purpose of doing testing. But you get the idea. We're trying to make sure that something's working. It's working as expected. It's meeting the expectations or requirements or goals we may have for it, that it'll work within an environment. HALT testing, for example, is we want to discover where and how it fails. What are the weaknesses of this particular design or this product? And so that we could go decide whether to do something about it. But the idea is that the information coming out of the testing is typically used to make decisions. Is it good enough, for example, or are we ready? Is it suitable to start production? Are we ready to move forward? Is this technology suitable for this environment? Those kinds of things we use that information for. Now, customers use some of this tested results to determine whether it'll be an appropriate solution for them, right? And so the data may be used internally, and that's where most of what we do is used, yet it could also be turned into a white paper that's shared with customers and with your sales teams. So it could have a pretty far-ranging set of uses if it's done well, right? I'm all too often here, I'm going to veer into some of my pet peeves and the things I really don't care for too much. But let's take a look at what we're doing. We're trying to get results. We're going to run, we're going to get some prototypes, maybe even only one. We might get samples. We might get coupons that have a particular coating on them. And we want to evaluate them if they will work in the environment they're in. Now, sometimes it's to discover what's the failure mechanism. It's and sometimes it's to see if it's an appropriate solution. Is our manufacturing, is our selection of materials and our manufacturing process going to create a durable result? Years ago, I got to evaluate different coatings on handheld gaming devices. And part of the process was to make sure that the coatings, the finishes that we're putting on it, would withstand all the normal chemicals that would be found in a home. Things like Coca-Cola, which we found to be a pretty aggressive element on all kinds of different finishes, perfume, hand lotions. There was a particular kind of sunscreen that had some strange active element in it that would bubble paint up on a surface if it wasn't done correctly. We used, I think there was like 14 or 15 different chemicals of various sorts, that from cleaners and and solvents to things like perfume and hand lotions. But also, we also then looked at it for abrasion, looking at fingernails and scratching and how well these finishes. We must have had 20 or 25 different ways to attack the finish, including sunlight, the UV radiation, to see if the color would fade or change, or crazing, things like that. And that was just for the coating, just for the finish. And that was just the environment that this product was going to be in somebody's home. And when you go to industrial ones, then you start looking at all the industrial chemicals and all the other elements that are out there that can attack your product. The environment is not just, airborne in the cabin or outdoor portable, as the military would grossly describe these big different kinds of environments. It's what's the day in the life of your product? What does it experience on and off all through its life, its useful period of time? The thing that we have the most trouble doing, and often don't have the time to do, is to create a set of environmental tests that replicate the actual environment. Now, in some products I've worked with, they would give out the earliest prototypes to their employees and say, hey, take it home, go use it where you would use it, play with it, don't show anybody, those kinds of things. But it was an intent to say, well, how is it handled in the rain? What is it when it's in the bathroom where it's very humid, and then you move it out of that into a coat pocket where it's very warm and bumped around, or dropped in a purse where it's jumbled around with everything else that's in there, or in a briefcase or wherever. But the idea of doing all of those random small environments or elements of the environment, different stresses, some of them are simultaneous, some of them are random, some of them are infrequent, some of them are, when combined, can be amplified. When you start thinking through just considering the finish on a surface, the number of stresses that could be applied either independently or together, it gets astronomical pretty quick. But we often pick one or two stresses, sometimes a few more, and use those results to try to piece out how it's going to behave in the environment. Now, underlying this is one of those great assumptions, is that, well, sometimes the sequence that occurs matters, and sometimes the piling on of different stresses, dropping something in a very cold environment when the materials become really brittle is different than when it's not very cold, where it's not as brittle. And so, do we freeze it first, or is there a freeze-thaw cycle that creates cracks? And then is it more susceptible to leaks or disruptions or breaks? I could go on. And I think get the point here, is that the environments we deal with are incredibly complex. And in the lab, we often simplify that to the nth degree. Now, the best environmental testing is the ones that are actually in the environment, ones that are with our customers. Yet we want those answers before we ship it to the customers. So therein is a dilemma. And thinking through how the environments stack up, how they interact, how they contribute to each other, how they amplify each other, is a part of designing the test so that you actually get some decent results. Now, one place we often go for all kinds of testing is to standards. IEC and SAE and CSA, and there's a bunch of regulatory ones, there's safety ones, there's procedures for making measurements, there's procedures for running a test. And I've been on standards committees, I've helped write some of them. There are plenty of variations out there. Some are freely available, others are extremely expensive. But the gist of it all is that the standards for your particular industry often is a good place to take a look at, well, what are the stresses and types of stresses or combinations of stresses that help us understand the environment, and what's the range of environmental conditions that we need to deal with, and how are we going to evaluate our product given those range of things. Standards often do a good job at telling us, here's the procedure: set up this chamber, set up these environments, set up this kind of conditions and preconditioning and so on. And then they give us a process to follow in order to apply a set of stresses. What it doesn't do a good job, though, is helping us interpret if those results that we get are meaningful or not. And we'll talk about that in one of the examples. But the idea here is that the standards have a role to play. This is how I did the test. This is how this laboratory conducted this measurement. And it gives us a touchstone so that it could be replicated if we needed to. We had a process to do it. Now you can do the same by thinking through and designing and writing out your test plan such that it's detailed enough that somebody else in another lab could replicate it. The standards give us they give us the standard, no pun intended, for how to be able to replicate the results that we get. And we can create those ourselves, or we could use the standards that are available. But the issue is that just because you pass the standard test, and it might, like in ICs, I remember they were using 77 samples drawn from 3 different lots and different periods of time, and all these things, and they would go through some set of environmental conditions, and it would have a pass-fail criteria. If you get through all these and they all meet the requirements or whatever that particular test was doing, then you could say it passed that particular standard. But when you ask, well, what does passing that standard mean? I mean, what does that translate to? What failure mechanism is not taking this product apart? And for how long will that actually be good in the field? How does that translate to out in the wild? And the standards typically, not all of them, but vast majority of them in my experience, fall short of helping you interpret what does the result actually mean. You know, if it's 1,000 hours under some set of conditions, what's the acceleration factor? What's the underlying failure mechanism that it's actually applied to? And if you're making an outdoor portable product and its most likely failure mechanisms due to dropping, sitting in a chamber at high temperature for 1,000 hours is not evaluating that failure mechanism. It's evaluating something completely different. Or is it related? How do they interact? And that goes back to this thinking through your design of what is the stresses being applied and how do they interact with your product, so that you can, at the end of that process, interpret it saying, oh, it's good for 1,000 hours at 85C. That's it. That's all it means. Or is there a particular chemical reaction there that you know the activation energy for, that you can then use the Arrhenius equation to interpret it out? But if you don't know what that reaction is, you don't have an activation energy. And again, we often fall into making assumptions around that at great peril. So be very specific of how you interpret it and why you're using that particular set of acceleration factors to interpret that test. The standards, in my experience, tend to stop just before it gets to the point where it says, what does this really mean? It just says, if you go 1,000 hours at 85C and it still works, then it's good. Okay, good for what is usually what I ask. And that about the last page of the standard, and they don't have an answer there for you. All right, modeling. Another reason we do testing is to, either build a model or verify one. We have an idea of the failure mechanism. Maybe we know it's a chemical reaction, but we don't know the activation energy. Well, we could set up an experiment, a test, to determine that activation energy. Oftentimes, whenever I've had to do that, is I get a hold of a chemist, because they know a lot more about how to determine the activation energy in a meaningful way than I do. But the idea is that we often do testing to create a line. For example, we want to create, we have a bunch of samples, and we're going to run them out to failure. And if they all get similar failure mechanisms, we could plot it on a distribution curve of some sort, maybe a Weibull distribution. If it's a nice straight line, we may be able to extrapolate that, to push that further out, and then relate the temperatures and stresses we're using. We could use an accelerated test design and determine the relationship between stress and acceleration. It allows us to create a model, or to verify a model, or to use an existing one to see where we fit on that particular structure. So a lot of our testing goes into either an assumed model or to create one. And again, thinking through those relationships and what information do you need to know that it's a useful result for that modeling result, for that model, and are we even in the right model? And we'll talk a little bit more about that in a bit. But the idea is that the data that we collect is used as the validate designs, predict performance, inform decisions. It's also used to help us understand the world that our product is going to be in, and how those are going to relate to the performance or the behavior of that product under all those different kinds of stresses and use conditions. All right, I get my cursor back here. There we go. But here's the rub. Of all the different kinds of testing you've done, are all of the results meaningful? I mean, have you ever had a result that just didn't quite make sense? This might be a rhetorical question, Mark, because depending on the type of testing you're doing. And if the idea here is that if we don't set out to understand what's the purpose of the experiments we're running, the use of these materials and resources, and if don't think through, well, what if one of them fails? What if I have a life test and I get 6 different failure mechanisms when we do the failure analysis? How can I interpret that? Do I have enough information to make a meaningful result out of that? Or is it too muddled up with insufficient data? What if I assume that I should have a linear behavior and it's not? I get a curve in this curve. Instead of a nice straight line on a Weibull plot, I get a curve. Well, part of it might be I'm using the wrong distribution, but part of it might be that it's not a linear behavior. Maybe I need some other phenomena to describe that curvature. So sometimes our results add more questions than they add information. And so part of the process of doing testing to get it right is to understand it's usually not a one and done kind of process. Usually it takes some understanding of what's going on, some preliminary work and understanding and characterization, validating and considering different models to understand what we're seeing, and then verifying those things, and then checking your assumptions all the way through. Then and only then do I think you have meaningful results. But it's usually not a quick, let's go through some samples in the oven and see what happens. It's usually not going to be terribly meaningful. It might provide us some more clues as to how to improve our testing and get meaningful results. But sometimes they just are a step in the process that we need to have. All right, so let's talk about assumptions a little bit. The number one question I think I've ever received in my entire career is how many samples do I need, right? And then we go up in the stats book and we find out that we need a gazillion samples. And they, in one place we actually calculated it out, and they wanted to verify that the beta of this Weibull distribution for this particular failure mechanism that was well known, they were doing some design changes, that the beta was between 2 and 2.1 or something like that, something ridiculously tight. Now, if you know anything about fitting Weibull distributions, the parameters are really difficult to get accurate. The uncertainty about them, the confidence interval about the parameters is generally pretty big. And in order to get it that precise, we needed something like 850 samples. Well, they only made 50 of these units a year, and they're expensive. So there was no way we're going to get 850 samples. So we tried a bunch of different things and finally got them, convinced them that knowing the beta between 2 and 2.1 was really not useful information for what we're trying to do. And so we ended up closer to 1 sample. Now, in another case, I was teaching a class and we were talking about sample size. And one of the factors in sample size is understanding what the population variance is. So if there's some measurement we're making, it's a combination of the measurement error, which we hope is small, less than 10%, but also what's the unit to unit variability that we would typically see in that population. And the smaller that variability is, the easier it is, the fewer samples we need in order to detect a change. And is it within spec or not in spec? Is it above a certain parameter or value or not, and so on? If the inherent noise, the variability of sample to sample is very, very small, 1 sample might be enough. And we calculated it out for this one particular electronic system where this company was using or designing, and they had a test that typically ran, and it was a very consistent process. And the variance was this, I don't know, it was part per million type variability from one unit to the next. And looked at all the assumptions, went through the measurements, and it looks like a really good measurement system. The gauge R&Rs were accurate, very, very capable, and worked out the sample size, and 1 sample was more than enough to determine what they needed to know. It really begged the question of why they're even measuring it anymore, because they were so far within their specifications and so tightly controlled that the probability of them ever getting out of it was exceedingly rare. But it didn't really cost them much to measure it. So it was a simple task, but it was amazing. But sometimes 1,000 samples is not enough. It really depends on what you're trying to accomplish and what's the risk involved. What's the purpose of this data set? How important is it? Is this a quick, easy decision? Do I do a little extra material for strength or not? Well, it might be $1 million question, or it might not matter much at all, one way or the other. So in the context, sample size and its calculations, while they are straight statistics in the vast majority of our circumstances, if we've got good inputs into the sample size, we can answer this question pretty cleanly. And then we run into, and this one's a question for you. What if, and I had a boss that told me this once, he says, well, the sample size is part the variance, which I just mentioned, and it's part how precise we want the measurement, the results to detect, what difference matters to us, the delta. But there's also this confidence in there related to, this is a sample and coming from a population, and how well does it represent the population? He says, well, what if you take that confidence and make it smaller? He says, well, we need less samples if we make it smaller. He says, great. Make it 50% or make it 10%. Make it really small, then we don't need as many samples. Now, what's wrong with that logic? If I take the confidence that my sample that I take, which is getting smaller with the lower confidence I have, that it represents this population. If I reduce it, what am I giving up? What happens to the results that I have? And I know there's some statistician types out there. I'm not seeing anything there, but I didn't mean to stump you on a sample size question. But if you reduce the confidence, the likelihood that the sample will give you results that represent the population diminishes to the point when you go below 50%, you've got less than a 50-50 chance that your results are anywhere near what the actual population is about. Now, if you're only interested in the total population of the 3 samples that you have built so far, and that's the entire population, and that's what you want to learn about, that's fine. Just go test those 3. But if those 3 are going to represent your 300,000 for production next year, well, now it's a different game. Now your sample size calculation needs to actually represent that larger population in the future. Yeah, I agree with you, Robert. Is just flip a coin if you're below 50%. Skip the testing, save all that time and energy. The other part of this is that oftentimes in setting up samples and doing this any kind of a statistical evaluation, when there's variability in our population, we often are asked or directed to take a random sample from that population. Well, we're often in the prototype stage and we don't have the population of production yet. But the hard part is that how do we make that sample representative of the variability we're going to see in production? Now that, a brain twister, right? And the idea is that the notion is that if we're worried about manufacturing variability for a particular failure mechanism, well, let's go get samples that are on the edges of our manufacturing variability. Let's go evaluate it directly and skip the random sample, but go do an experiment that looks at the extremes to get a better understanding of how our product will perform given the variability that's going on. But that's just one seed of this. The issue of picking a sample that is representative of the population and of the failure mechanisms that we're interested in, the variability that impacts those mechanisms, that's a brain teaser in just about every circumstance and deserves a lot of attention and time to sort it out. I see that Mahindra, the 60% confidence used in some JEDEC standards. It's used in a lot of standards. And the intention there is to keep the sample size low. Remember, many of these standards are written by a committee and they all have to come to a consensus on it. And if one of them says, well, our products are expensive, we can never get 22 samples. Well, if we make it 60% confidence, we only need 3 samples. But what kind of results are you really getting? How useful are they? If I'm making $1 million decision, do I want to be vaguely, sure that my sample results are representative? Is 60% enough to put your money on it? In many cases, not. Now, sometimes you just don't have a choice. You don't have the samples or resources to do more samples, but understanding the risk you're taking is appropriate and should be communicated along with the results. You can't just say I passed the test when you have a 60% confidence. Well, the sample group that we drew passed the requirements. The chance that that represents the population is a little better than a coin flip. So be sure to communicate the assumptions that are being made and the risks that are being taken. Now, one of the things is failure mechanisms. Just about every conversation I have with somebody that's setting up testing is, well, what failure mechanism are you interested in? Right? Is it wear? Is it abrasion? Is it crazing? Is it bubbling of a finish? Is it creep or mechanical wear? Is it chemical corrosion? What's the mechanism? Going to the lab to go do testing for Halt to discover how a range of different stresses could excite a mechanism is great. That's a good purpose. But once you have a mechanism, you want to know, is it going to last long enough in our application, or is our design changes going to make it better? Then we need to understand that mechanism, not the mode, not the symptom that this product sees. Let's say it doesn't turn on. Well, that could be a litany of different mechanisms at play. And is it induced by vibration, or is it induced by heat? Is it induced by voltage surge? Is it induced by, I forgot to plug it in? What is the mechanism? What is the understanding of that? From there, we can start making better decisions about how to go evaluate it and test it. And so the hard part here is that some mechanisms don't behave the same at different stress levels. They're not a linear behavior. They may have a peak of activity and acceleration at a nominal temperature and then float away or be almost non-existent at low or high stresses. Or they could be only really excited when there's a particular other element or other stress available. Understanding the mechanism, understanding the failure mechanisms that you're interested in is essential in order to make sure that you're addressing the appropriate assumptions throughout your test design. Let's see a couple more comments here. Yeah, the variability is a key one. When we're looking at, say, crack propagation, one of the things that occurs within many materials is that if it's got impurities in it, or it wasn't cured correctly, or formed correctly, had some kind of mechanical or chemical defect within its structure that allows it to initiate a crack, and then it takes off and moves pretty quickly. Crack propagation has to start somewhere. And depending on the materials that you're using and using the appropriate designs, you can minimize the ability for the crack to even start. But then it's a separate problem, separate failure mechanism as that crack propagates across the structure that you're interested in. There's other issues like that, where there's an initiating event that has one underlying phenomena, and then there's a second phenomena that then allows it to propagate to failure. So sometimes it takes the coating, or like the bearings, the lubricant is broken down or leaks out, or it degrades as a first step. Then the metal of the bearings start to wear, and then we lose the bearing. But as long as the lubricant's there, the metal of the bearings usually is well protected. And so think through your mechanisms. Are there 2 or 3 steps in that process? And is the testing we're doing relevant to all of those steps? You know, if we're testing a seal on something, if that seal needs to have some like physical motion, say a coefficient of thermal expansion induced strain across it that causes the fail, or maybe it's a temperature related that makes it brittle, and then a shock that cracks it, and then it'll leak at any other temperature. What's the sequence that's likely to cause this chain of reaction that causes the failure of the system? But there may be multiple mechanisms at play. right, acceleration factors. The very first reliability test I did was an accelerated test, life test, and it was a chemical process. That was our failure mechanism. And so my first thought going through the stats books was, oh, I'll just assume an activation energy. And one of the folks on the team is a chemist. And she said, no. Take a look at your calculations here. If you miss that by 1/10, it makes a dramatic difference in the answer. Even with the exact same data, if you assume the wrong activation energy, it will be all over the map. So let's do two things. She said, one, I'll go in the lab and I'll use this process that we chemists use to estimate your activation energy for this phenomena. This is an oxidation process for this polymer chain. And she did some calculations, she did some experiments, and said, here's what your activation energy should be. This is what we think it is. And we set up the test so that we had enough information from the test result in order to determine the activation energy. Now, neither method's perfect, but if they agreed, we were pretty confident we got the activation energy right and our results were clear. If they were different, it gave us a range over where we expected that energy to be. And then we could say, well, here's the level of uncertainty we have given this range of activation energies that we think are at play. And there may be other factors at play here also that we need to get better at. But we designed the test with separate experiments to help, but with also in the test itself, so that we could check a whole series of assumptions that were within the design of that experiment. And so it allowed us, one, we had lots of samples, had plenty of resources to do it, and it was a very important decision, so we got plenty of support to make it happen. But the idea is that if you don't think through, how do I check my assumptions, it gets really tough to do it if you didn't design the test appropriately. So one of the things I like about Wayne Nelson's book, Accelerated Testing, is that just about every one of the processes for doing life testing include a section of assumptions, usually related to the statistics, but they clearly state what are the underlying assumptions that you need to be aware of. Now, sometimes they said these are, it's an assumption, but it doesn't really make a huge difference on the results, but you need to be aware of it if it gets really bad, if it really doesn't fit. In other cases, this is a very serious assumption. If it doesn't meet this criteria, then your results are not reflective of what's really happening in the environment you're dealing with. So part of acceleration factors is our translation from some applied stresses to what we think is happening in the field. And it's a way for us to cheat time, but it has a significant cost. If we ignore those assumptions, we'll get a number at the end of the day, yet the chance that it's meaningful is very rare. Now, some of these other assumptions, and Wayne talks about it in his book, is the thought that your stresses act independently on the stresses or on the failure mechanism, that you don't have a failure mechanism that acts differently at high stresses, so it masks the one that you're interested in, or shields it, or sedates it, for lack of a better word, but calms it down, for example. And so that it looks like it's going to last a really, really long time at use conditions, but we don't have this dampening effect of some other phenomena occurring when we're at higher stresses. So thinking about how things interact and how they behave over the range of stresses we're using. One of my favorites was somebody said, well, we have this material and we'll use water, for example. Well, once you go to steam, once you you evaporate the water off, or you go below freezing in it and it expands in the ice, now we're dealing with a completely different set of stresses. And so some standards say test between 0 and 100 degrees Celsius. Others say go to -40 to +150. Now, the wider that range, the behavior of moisture, of water, of H2O is deliberately put into ice and deliberately put into steam or into gas. In other cases, we want to avoid that because our use conditions don't include that wide of a range. But be careful about the materials you're using and how they behave over different stress levels. If you go across a phase transition, you can be pretty sure it's not going to behave the same way it would at nominal conditions. All right, let's take a look at a couple of examples. And hopefully this just sparks a few of them for you to bring up. Now, I mentioned 85 right off the bat here. So here's a question for you. This is a set of conditions, 85 Celsius and 85 RH. There's chambers, temperature, humidity chambers out there. There's all kinds of requirements and standards that say you need to do 85. But let's say you do 22 samples, which gives us 90% confidence that we're at least 90% reliable over some period of time. And we run this test at 85 for 1,000 hours. What does that mean? What does that translate to? What is, if you use this for your products, how do you interpret those results? And I've seen this 85 for electronic components, for plastic encapsulants, which is where I think it came from originally. I've seen it for solar panels. I've seen it for powder coatings on metals. I've seen it for corrosion resistant schemes. I've seen it for, well, that's just, it accelerates temperature and humidity at the same time. And so we think it means something. I've seen it for fungus growth and attacks. I've seen it for handheld products. I've seen it. I don't know. Somebody created a chamber that could do this, and they decided to create all kinds of standards that uses it. I don't have any evidence that that's where it came from and why it's so widespread, but it seems suspicious that it's in so many different industries and so many different places. Yeah. Now, if you compare it to your field use and you have time to failure in the field and you have time to failure in your testing examples, in your 85, you may be able to come up with an acceleration factor, assuming you get the same failure mechanism, right? But let's say you run a set of samples for 1,000 hours. And if you don't have an acceleration factor, which most standards don't provide you, what does that mean? It's not a rhetorical question. It just means that you have 22 samples that are able to survive for 1,000 hours at 85. That's all it means. Does it mean that you get 2,000 hours at 45 C and 85 RH? I don't know. What if I don't get any failures? Does that mean it's going to last for 1,000 hours with 90% confidence at 90% reliable over 1,000 hours if the conditions are 85? Now, without the acceleration factor and without understanding the failure mechanisms at play and how the temperature and humidity excite the failure mechanisms we're interested in, it's really hard to get a failure or acceleration factor and interpret it in any meaningful way. But I've seen it in so many different industries, and too many times it's listed on the data sheet saying we survived this, we did this, and it's 85 is just one of many environmental stress screens or stress tests that are done, test to pass for some defined test set of conditions without any relevance to failure mechanisms that are of interest. If it can't be clearly articulated, and here's the connection, here's the science and the chemistry and the physics of how this test condition relates to this failure mechanism, well, then that's a sign of a really poorly run test or design test. So think it through before you go off and do one of these. Make sure that you can interpret it. Yeah, you see it as a checkoff list for procurement folks. Oh, they ran a bunch of standards and they passed. Well, is that really relevant? What if I pick a dozen different tests that I know I can pass and I skip the one that is really going to damage my product and reveal its weaknesses, but I just passed 12 standard tests? Sales guys love it when they do that. Have testing. Here's another example. Let's see if I get my pen to work. I was practicing before we got started here, so hopefully I got it to work here. So let's say you got, oops. Yeah, put some text on here. This is time, oops. And this is a CDF. This one might be easy. So let's say I have a product that gives me over time, it gives me a particular slope, and then my failures are occurring at a much steeper rate. I call it a hockey stick, but what is that in? How do we interpret that? This is an easy one. I like your comment there, Robert. Yeah, it gives us some unknown level of confidence that our product might work at some set of conditions. All right, so let's say I run a life test. I'm getting failures, right? I got a handful of failures that occur, and then I got this. What is that? What is a way to interpret that? Bimodal, yeah. We've got, if you're lucky, there's these items that failed are the same failure mechanism, and they represent one slope. And I'll use a dash line here. And it's worth checking, are these failures that occurred the same, but different than the other one? Or did some phenomena occur? Did we go through some phase transition, or did we go through some hardening process or something else that occurred? But generally, when you see something like this, it's a change in the failure mechanism. There's a difference, a bimodal. And sometimes you see three-way ones that are even more difficult to interpret. But that's an easy one, right? Let me clear that. And let's try another one. Let's say, is everybody familiar with residuals when you're doing regression analysis? ALS. Residuals are the difference between the data and the model. So like that Weibull curve, let me do a quick, here's my model, here's my Weibull distribution, and I have data points that are some distance away, right? And so the residuals, oops, let me get a different color so they show up. Doesn't do good to pick a different color and it's the same. So these little distances, this one's way out, these little distances here is the residual from this data point to the model, what it says. Now, ideally, we want our residuals to be very, very small. And we want them, if we shook them all off of this little line and say, rotated this up and piled them up onto a distribution, we would want a nice, tight, normal distribution. Now, what if it's not? What if the residuals are not a simple, small, normal distribution about our model? What does that mean? I don't think you signed up to take a stats data analysis statistics test, but this is important. If I'm running, and one of the, many of the most popular reliability software packages don't give you residuals, or at least don't give them to you in an easy format that you can interpret. But ideally, if I'm plotting, say I've got time to failure and I'm plotting the residuals, this is those differences on my lower graph here. If I get just a nice cloud, kind of above and below, such that if I tipped it up and piled them all together, I get this nice normal distribution. That's great. Then I know that my model reasonably describes the phenomena I'm seeing. But what if the longer the time goes, the bigger the residuals get? What if there's this pattern where they're flaring out as they go forward? Or they have just a diagonal line across our model. You know, when you plot it, it's a curve or something like that. The idea of looking at the residuals is a way to reflect on, is the data I'm collecting represented well by the model I'm choosing to explore? So we could go create a CDF and a Weibull plot and create those nice hockey stick kind of lines and say, yeah, we probably have two failure mechanisms. But if the residuals are all over the map or showing some other behavior, it could be, just as you're saying, Mahindra, that there's some other factor at play. There's some other stress that the model is not accounting for, right? Maybe as over time, there's some other phenomena that's occurring that's creating the probability of failure becomes much more random, much more, it changes the data set that we're getting. And if it's not built into the model, we can't account for that variability. Now, a part of doing experiments is that the results are reflective of what we wanted, of our understanding of that reality. And so by looking at residuals, it allows us to do, one, good data analysis, but two, it allows us to probe, are we getting the appropriate model? Are we understanding this phenomena correctly? And so let me clear that off. And I think I got one more example here for you. Let's see. Get rid of that. There we go. All right, success testing. Very economical, very easy to do. If you got to have all kinds of assumptions lined up before you can do it. You got to understand what duration you're using, that your samples are representative, all kinds of other things. But I use 22 samples because it relates to the binomial equation, meaning that you have a 90% confidence that if you pass this set of conditions, that you have 90% reliability over that set of conditions. And sometimes they're accelerated. But the idea is, if they all pass, what does it mean? But if one fails, what does it mean? Now, if they all pass and we are applying stresses that we have a good understanding of how it relates to the failure mechanism at play and how to translate that set of stresses to the use conditions we have, it means that we have a 90% confidence that we have 90% reliability for that failure mechanism or that set of conditions. But if one fails, this is my last trick question for you here. If one fails, what can we say? Nothing. The results are mute. They have no results. 22 samples with one failure means that you have 1 out of 22 fails. Now, the confidence level drops, but should you recalculate it after the fact? Is that ethical? Is that meaningful? Right? You've got information now that you set up a test using this pass-fail criteria and binomial equations so that you get the minimum number of samples. You've done the due diligence, you got all this information. But what it means is that we do not have evidence that our process or samples or product or design or whatever meets the criteria of 90% confident, 90% reliability over this duration. It means we don't have it. It's a binomial test. It's pass or fail. If we pass, we can say we have that confidence that it's at least 90% reliable over this confidence. But if one fails, it just means that we cannot say that. It doesn't mean that it's 85% confident. You could go run those calculations, but that's not we already have the results. And the design of the test doesn't allow you to recalculate it after the fact. I mean, it's similar to saying, well, what if I just rerun the test, one more sample and it passes? Now I've got 22 that pass, but I'm ignoring the one that failed. Is that a meaningful result? No. We've taken samples and we're evaluating them on a pass-fail. And so when doing these shortcuts of sampling and testing is be very aware of how to interpret it when it doesn't work. What are you allowed to say with rigor versus what you're not allowed to say? And so think through for any kind of testing you're doing in the design of it. Well, what if we lose a sample? We drop one on the floor and it becomes damaged, or our chamber doesn't work for a week and it overheats everything. Or what happens if, go through that risk analysis for your testing so that the results that you see actually can be interpreted well. And think through the scenarios. And some of you with great experience already know a lot of the different ways these things can go wrong. But, take a look at the range of possibilities of as you start designing your test, such that given the various scenarios and risks that will inevitably occur, allows you still to get good results. And then the basic idea here is if you do it well, right, then you can inform those decision makers with useful information. Doug, I don't think so. There are ways. One scenario I've talked to a couple of statisticians about is that now you're no longer doing a binomial test. You have one sample that's failed and you have some duration on it. Now continue running until you get enough failures that you can fit a distribution to it, right? Now to fit a Weibull distribution, the guideline that I've heard is that you need at least 5 failures, time to failure pieces of information out of 20 samples. So if I start in with 22 samples, keep running the tests until I get 4 more failures and then fit a curve to it. It's not great. It's the confidence around your beta and eta for a Weibull distribution will be really large, but you can salvage that information if you switch it to a different kind of test, to a variables test. Pass-fail tests are pretty finicky from a statistics point of view. And once you learn some of the information, then the basis of that test changes. So running the 21 samples longer or running, starting another sample pretty much invalidates the premise of that binomial test when you started it. So be very careful about that. All right. So that's the formal part of the talk or presentation. Thanks for all the inputs here and comments on the chat. But, if you've got questions or see other thoughts here that you'd like to discuss, I'll hang on the line here and be happy to do that. I know that you've got the rest of your Tuesday to go after, so I won't hold you back. And thanks so much for coming in. I thought about putting a bunch of formulas in there, but I think thinking through the process we use to design and execute tests is what's fundamentally a part of doing effective testing. So that's where I tended to focus today's discussion on. All right. Well, I'm going to go ahead stop the recording, and thank you all for showing up today and participating. And